Hello, continuing on with the 2022 Oxford Pat, we're up to question 16. So we've got f of t is this, g of x is that. Consider the inequality, the differential of g of x is greater than that integral of f of t. For which values of x is this satisfied? Right, okay, so let's differentiate g of x then. We're going to get 3 over 2 times 3 minus 2x. And that needs to be greater than, so we're integrating 4t. So that's going to give us 2t squared. And that's from x to 3 over 2. So what we got there, 2x squared, and then we'll have 9 over 4 multiplied by 2. So minus 9 over 2. Right, so that's given all of that. Let's get rid of some 2's then. Multiply everything by 2 and deal with that bracket. So we got 9 minus 6x has to be greater than 4x squared minus 9. So 4x squared plus 6x minus 18 has to be less than 0. We got a factor, we can take a 2 out of all of this. I'm going to move it up here just because I don't want to scroll down. So 2x squared plus 3x minus 9 less than 0. That is that factor in? We'd have, 6 minus 3. So yeah, 2x minus 3, x plus 3 less than 0. So we're going to need a positive quadratic less than 0. So it's between the roots. So x needs to be between minus 3 and what's that, 3 over 2. Right, yawn, I think, is the only way to describe that question. But still, that's another one out of the way. All right, looks like we're on to a geometry question, which is usually a good sign. 4 circles, a radius r1 inscribed inside a circle of inside a square, of side 4r1. Right, so this picture, circle, 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 small one stuck in the middle. Right. What is the radius r2 of the largest circle that can fit in the space? Right, okie dokie. Right, this is giving me memories of a 2006 Pat question where we only had 2 circles, but I ended up doing something much like this, of working out a path from top to bottom and then saying, well, top to bottom is 4r1, and that is going to be equal, we got r1 there, so that's 2r1 plus r1, so 2r1 plus 2r2, 2r1 plus 2r2, multiplied by this is 45 degrees because it's all symmetrical. So that will be multiplied by sine of 45 degrees, which is a root 2 over 2. So we could certainly solve for this. That's going to cancel with that and that. That's going to cancel with most of that. So we've got 2r1 is equal to root 2 r1 plus, divide by the root 2 over here is what we really want. R1 plus R2. So we've got that R2 is going to be equal to R1 root 2 minus 1. Right, having worked through that though, I think I've just seen a better way of doing it. But what I'm now thinking is, well, actually all we care about is this bit here, don't we? We just care about that square. We know that we've then got a square of side R1. We don't need to deal with all the rest of it. We're saying that R1 squared plus R1 squared is equal to R1 plus R2 squared. So that means root 2 R1 is equal to R1 plus R2, and then R2 is R1 root 2 minus 1. So we've ended up in the same place, but slightly easier. Right, so that's better just looking at this square here, but it was hardly a lot of work either way. So that's the first bit. Right, now B, if 8 spheres of radius R1, right, okay, arranged inside a cube, still, right, we've got the same, oh, well, it's a cube, but it's still a 4R1 side. What is the radius R3 of the largest sphere that can fit in the middle? Right, so they've stepped it up somewhat to go, but I think this method actually is going to be really useful for this. So if we've got, let's just think about the cube first of all. We've got this cube and we've got 8 spheres in it. So we're going to more or less be putting these 8 spheres into 8 mini cubes inside all of this. So we're going to have, yeah, 1, 2, 3, 4, and then it'd be 5, 6, that'd be number 8, and 7's buried at the back. So we've got all of those. The sphere, the little sphere, is going to be right in the middle. And we want to join up then. So if we joined up, let's change color here, just so it makes sure we're visualizing this. So let's get a diagonal here. So this diagonal goes from corner to corner, opposite corner, and it's going to go through the center. So what is that doing? The center is going to be, so if we continued that cube down, that is going to be sitting at that bottom, is going through the center of cube number 1. We're then going to be hitting at the back, that's going to be the top edge of cube 8. So we are going to be going through to the sphere here and the sphere down at number 8 with the little sphere in the middle. So yeah, that's what's happening there. We've got big sphere, little sphere, big sphere. This is on the diagonal. Actually, that's not touching, that's outside of there. That's the opposite corner. So I'm going from this corner here down to that corner there, which is this point here going to this point here. That diagonal is going through the center of these 3 spheres. So we can split all this up again because these are in quarter distances. That's 1 quarter, that's the next quarter, that's the next quarter, and that's the next quarter. So the diagonal of the sphere as a whole, diagonal of the cube as a whole is, we got 4r1 there, 4r1 there, and 4r1 there. So doing 3-dimensional Pythagoras, we're going to have the square root of 3 lots of 4r1 squared. That is the total diagonal of the cube. You divide that diagonal of the cube by 4 because we just want to look at that bit of it. And that will be equal to r1 plus r3 because we're going from center to center on the 2 spheres. Oh, this is great. So that 4 is going to cancel with that 1, is it? Yes, it is. Yeah, because that's going to be 4 squared square rooted. So we've got root 3 r1 minus r1. R3 is root 3 minus 1 r1. Yeah, that was really nice. I like that. I may have been saying sphere sometimes when I meant cube, but I'm sure the pictures would make it clear, you know, what I was doing all the way going through. Yeah, anytime I was talking about a diagonal, if I just have a feeling I was saying diagonals of spheres when obviously I would have meant diagonal of the cube. But yeah, all these diagonals all referring to the cube. So yeah, I really like that. I think it would have been quite difficult to do this approach of doing the top to bottom, you know, this thing that I did here. So this was a nice way of splitting up the 2-dimensional puzzle to then sort out the 3-dimensional puzzle. So yeah, that is a challenging geometry question, I would say. That's quite tough for 6 marks. But yeah, it's nice to have something like that. All right, consider this function where we got various positive constants, p, q, and r. Well, everything's positive. We've got x greater than 0 as well. So find an inequality satisfied by p, q, and r in order for f of x to have at least 1 real root. Right, so we need, well, let's try and solve all of this. Well, we can multiply through by those x cubes as well. So anyway, let's get this all on the flat. So we want minus p over x cubed plus q over x squared minus r over x to be equal to 0. Now I can scroll down a bit. So let's multiply everything by x cubed just to deal with all of these fractions. So we'll have minus p plus q times x minus r times x squared, and that is equal to 0. So we want to have well, yeah, we need our b squared minus 4ac to be greater than or equal to 0. So we need q squared, so minus 4 times p times r to be greater than or equal to 0, and that gives us our root. Right, so that was good. Find the relationship between p, q, and r in order for f of x to have exactly 1 stationary point. Right, So f dash of x then, if we differentiate, is going to be 3p, because we get the minus is going to go away, to x to the minus 4. Then we're going to have minus 2q x to the minus 3. And then we're going to have plus r x to the minus 2. And we want one stationary point out of all of this. So let's do the multiply through by everything again. We want one station, so we multiply by x to the 4. But then I suppose we could divide. Do we want to multiply by x to the 4? Yeah, let's multiply by x to the 4. So we've got the 3p minus 2qx plus rx squared is equal to 0. And we want one solution to this. So we're going to need that b squared, which is 4q squared, minus 4 times a times c. So that is 4r times 3, 12pr. 12pr. And for one solution, we need that to be equal to 0. So that's good. If the relationship of the previous part holds, so this one, so that exactly one stationary point exists, what is the nature of that stationary point, and at what value of x is it? It's not necessary to work it out. Right, so, well, we can divide by we can divide by 4. So we're going to have that q squared is going to be equal to 3pr on all of that. At what value of x expressed? Right, so, what's that telling me with all of this? That's going to be then, actually, that's the bit that's not of any use. I don't know why I'm thinking about that, because x would then end up being minus b over 2a, because we've now got plus or minus nothing. So it's the other part of the quadratic formula. Yeah, so this is all irrelevant. We don't really care about that. So minus b, that is 2q, and then 2a is 2r. So x is q over r. Right, okay, that's good. Then, so what are we now saying? We need the nature of the stationary point, and they're claiming that we can do this without having to work out the second derivative. Right, that's going to be interesting. So let's try drawing this out then, do we? X has got to be positive. I mean, what does this thing look like? If we, I've got it written here anyway. I've already copied it down, haven't I? So we've got some thing going on. If x is 0, where is it starting? If x is 0, then we've got the minus infinity, haven't we, on all of this? Yeah, because we've got, this is going to be bigger. When it's really close to 0 is what I'm really saying. So it's slightly more than that. It's like x is equal to plus 0, I think is what I'm getting at, really. So this term is going to dominate the first one, the minus p over x cubed. So y, or well, f of x is going to be equal to minus infinity. So we only have to do this for positive x. So we're going to be starting here. We've only got one turning point. So when x is equal to, well, let's say positive infinity, then f of x is going to be equal to minus nothing, plus nothing, minus nothing. But the biggest nothing is going to be that one, because we've only got an infinity on the bottom, not an infinity squared or infinity cubed. So we're going to have minus nothing. So we're going from there to there with one turning point. So it must be a point of inflection then. Because if we had a maximum, we're stuck. We can't have a, if we had a minimum, we'd be stuck, because you'd have to have both to get to the other. So if we have got a turning point, it's got to be a point of inflection. Otherwise we can't, we can't do it, can we? So it's going to have to be, however that would work, it's going to have to be a point of inflection. So yeah, that's going to be that. Right, that was difficult, that last part. I suppose they gave us 3 marks for it. I mean, the first 2 parts were fairly straightforward, but the last part was quite tricky. But it's another nice question. This is a good paper so far. I'm quite enjoying this one. That was question 18. Right, following Bohr, we assume that a hydrogen-like atom may be modelled as a single electron, mass m, charge minus e, in a circular orbit around a much more massive nucleus, charge plus Ze. Oh, I see. Oh, hydrogen-like. So that's why I've got a Z there then. By balancing forces, find the speed v of the electron in terms of its orbital radius. Right, that's just going to be a circular motion thing, isn't it? So we'll have that mv squared over r is equal to ze squared, because that's the product of the charges, divided by 4 pi epsilon 0 r squared. That's just sticking it into Coulomb's law. So that's going to give us that v is equal to the square root of ze squared over, we're going to have 4 pi epsilon 0 mr on the bottom. So that was fine for starters. Show that the total energy of the electron is equal to the negative of its kinetic energy. So the energy is equal to kinetic energy plus potential energy, which is a half mv squared plus u, half mv squared. So we've got a half times, well, m times v squared is going to be the thing under the square root without an m in it. So that's ze squared over 4 pi epsilon 0 r. And then u is this thing they've given us here, minus ze squared over 4 pi epsilon 0 r. How's that simplifying? Oh, we got half of something minus a whole of something is equal to minus a half of something. So that is equal to minus the kinetic energy. So yeah, that actually works out fine. I thought we were going to get really stuck there, but that just drops out just by putting the numbers in. We're not really doing very much there. Assuming that for the electron, the product mvr equals nh bar, where n is an integer and h bar, pronounced h bar, is a constant, find an expression for the electron energy in terms of n. Find an expression of the electron energy in terms of it, which does not depend on either v or r. Right. Right. So anyway, we had our energy. So the electron energy we've just said is minus a half ze squared over 4 pi epsilon 0 multiplied by 1 over r. I've separated the 1 over r off because that's what we want to get rid of. But we don't want to put v in it. So we've got the mvr equals nh bar. We also know what v is. So that is m, it was the square root of ze squared over 4 pi epsilon 0 rm. That was that, multiplied by r is equal to nh bar. So this is going to give us an r that we can then eliminate in the other one. Right, okay. This is, let's square it. It's going to be so much easier if this was squared, wouldn't it? So let's get rid of that and that, put that there, and that there. Because then that will cancel with that, that will cancel with that. And we're going to have that r is equal to n squared h bar squared 4 pi epsilon 0 divided by mze squared. And then we just put that into here. That's definitely what I wanted, wasn't it? An expression for the electron energy in terms of n does not have v or r. Well, it won't do. So E will be, oh, this is going to be a right mess, isn't it? Minus a half ze squared. Oh, we're going to have things cancelling. 4 pi, where are we? Epsilon 0. And then this 1 over r. So that's an m. Oh, no, we're not having things cancelling because we're doing 1 over r. N squared h bar squared 4 pi epsilon 0. Right, so we can certainly put down some of this as being squared because we've got a ze squared over 4 pi epsilon 0. That's all been squared, and we're left with a, what are we left with? An m. We've got that m there. That's done the top. and we've got a minus sign. And then we've got a 2n squared h bar squared on the bottom. Right, so that's that. Geez, and it's got no r, it's got no v. Everything seems hunky-dory on that one. Right, so that was quite odd. That was more for 2 marks than the others were for 6. Right, now part D. If e for n equals 1 is that, what is e n equals 3? Okay, right, so we've, oh no, it's not as simple as that, because that's hydrogen and that's helium. So Z has doubled. Z has gone up by 2. What's happened with N? N has gone up by 3. So that means we've multiplied by 4 because it's Z squared. But it also means we've multiplied by 1 over 9 because we've got a 1 over N squared. So we're going to have 4 over 9 times whatever it was, minus 13.6. So calculator time is going to be giving minus 6.04 electron volts. Right, okay, that last bit was easy, but there were parts that you could get tripped up on. So whether you've spotted that both Z and N have changed. But yeah, that was another involved question. That wasn't easy, but again, it was achievable. They're really pitching the questions nicely in this paper, I think. But that's been a long enough video on this one, so I'll leave that there.